Today we're going to talk about thermal cameras, where they're useful and explicitly where they're not useful, where they can produce bad data that ends up being accidentally misleading or just isn't useful towards the conclusion anyway. Obviously the catalyst for this content was the Austin Evans comparison of the two PlayStation models. We have the second model coming in. We're actually working with Digital Foundry to borrow theirs. They haven't disassembled it, so we'll be able to look at it in an untampered scenario. And we'll be doing the testing with our usual approach to it. But until we get both devices in side by side, we do have a new digital one as well. That's the older model. Until we have them both in hand, we can't commit to any kind of comments about what the performance difference actually is. So this video is not a response to Austin's work or his video or his conclusions. And in fact, it's possible that his conclusion was correct, that the newer device may be worse. We'll need to test it to find out for sure. While his method to get to that conclusion was, we think, just not particularly useful. Thermal camera data of the back of a box, it's just not going to tell you anything. That's the plain simple truth of it. But we don't think Austin was trying to do Sony dirty by showing one versus the other on a thermal camera. And we don't think that he deserves the insane amount of hate and attention he got for the piece. It's unbelievable how people responded so completely irrationally to his content piece, where even though we professionally disagree with the approach to the testing, it doesn't deserve that reaction that it got. It's insane. There are a lot of correct ways to test a device. There's not one correct way to do it. So don't get us wrong there. But there are incorrect ways to do it, or minimally ways which produce data which is not useful towards supporting a conclusion. So that's what we're going to talk about today. Before that, this video is brought to you by Kioxia, said to be the original inventors of NAND flash memory and formerly known as Toshiba memory. Kioxia's XG6 M.2 SSD is a high-end NVMe SSD claiming up to 3180 megabytes per second read and 2960 megabytes per second write speeds sequentially, and it's ideally used in high-performance gaming PCs or power-conscious laptops. The XG6 is available up to 1 terabyte, and the company also has its BG4 SSD in a much smaller M.2 2230 form factor for up to 1 terabyte of ultra-compact storage. Learn more about Kioxia at the links in the description below, including about their enterprise storage products. This content has some cool experiments in it where we're going to show you thermal camera images of the exterior of devices versus internal die readings and measurements. So this will allow us to really put numbers to it and show how a thermal camera reading of, say, a heatsink on top of a CPU can be misleading compared to the actual CPU temperature, wherein the heatsink being cooler really doesn't necessarily mean that it is a better heatsink. It could, but it probably doesn't. We'll also show the same with cases, which is more similar to this scenario, where you're looking at a closed box, got a lot of steps between the outside of the case and the device ultimately being cooled. And so we have some experimental data to show you what the gap looks like and why a thermal camera isn't particularly useful. Thermal cameras can be useful, though. We'll talk about that too and where they are best deployed. But to, again, recap the points that we really need to get across before we get started. One, the reaction to Austin's video was too far in the direction it went. It's insane. We've been through that too. It sucks. And it's not productive for anybody to attack someone like that, because you're not going to get them to say what you want them to say. You're potentially just going to put them in a corner. So not really the right reaction. And we're not talking about just criticism of an approach or well-expressed criticism of how someone tests something, but rather the farrago that it devolved into, where it just ended up being chaos in that comment section. And that's not productive for anybody. It doesn't achieve what people want. So we do need to address that. Point two, again, it is possible to reach the correct conclusion with the wrong formula, just like in math. And then point three, for us to make any comment as to which device is better or worse, if the new one, the cooling solution is better or worse, we need to wire it up everywhere that we can and test multiple things so that we can really get a full picture of it. Because it's possible that one part's better, one part's worse. And if you don't have things like control the fan speed, for example, control where you're measuring, if you're trying to use a thermal camera and it's at sort of various distances with no real control there either, the numbers aren't comparable. So for testing, some method needs to be applied. We have a pretty good test plan for when we get the two devices. Probably we're going to do some testing stock, and then we'll do some testing where we take the same base hardware and swap the coolers so that we have a true like for like. What this also does is allows us to control for where specifically the thermocouple is wired, so we don't have it off by, say, 0.5 millimeter on one versus the other, because that'll affect the reading. So we'll do all that. We'll talk about it in the piece coming up. But for today, let's focus and get started on talking about thermal cameras and show why they aren't useful in some places where companies like to use them. This isn't about Austin's content. This is about Intel and AMD, who have set the stage and set the example to tell everyone, you should use thermal cameras to measure our CPU performance because that's what makes us look the best. Of course, the real reason a lot of people think they want to know the temperature of their console is because they want to be told that the one they chose is better than the other one. They want retroactive confirmation of bias. And it's very unfortunate. It's the same reason people watch video game reviews. It's so that they can be told that they made the right choice. But ultimately, there's a few things that people in this particular camp don't really understand, which is that there's no one temperature of the console. There's no temperature of the PS5. Your PlayStation 5, your Xbox, it is not a temperature. It's not 54 degrees. Just like your computer, you can't say my computer is 60 degrees. That's not how any of that works. There are a lot of different things in each of those devices, and each of those things has its own temperature, which is largely dependent on how it is directly cooled and what processes it is responsible for handling at any given moment. As far as the quote-unquote temperature of the PS5, again, it's not just a temperature. There are various things. There's the SoC, there's memory, there's MOSFETs, there's capacitors, and they all have different tolerances, just like they do in a computer, like we've shown in some of these B-roll shots. An inductor, for example, could sit at 100 degrees and be technically fine because it's just a copper coil inside of a box. It doesn't really care that much how hot it is. Whereas the SoC at 100 degrees, the same temperature, would minimally be throttling, if not just straight up shutting down because of hitting TJ max. And then there's capacitors, where you have completely different tolerances and temperatures. You might have a really high-end capacitor that's rated for 10,000 hours at 105 degrees, or you could have a really low-end one that's 2,000 hours at 85 degrees. These are massively different, and because the ratings are so different, the temperature that it is has different meaning. So if we probe a capacitor and find that it's running at 85 degrees, if it's rated for 85C at 2,000 hours, then now we know kind of the limitation of life of that capacitor at that temperature. Whereas if it's 10,000 hours at 105C, but it's measuring 85, it doesn't matter so much that it's 85, at least not nearly as much as in the first scenario, because it can handle it. It's rated for it, it will live longer. As an extreme, this is why we present both the CPU and the GPU thermals in our case reviews, and we collect more data than that too that we don't publish, like the PCH temperature, for example. Cases often don't cool evenly, so you end up with something like, let's say, an NZXT H500, where the case is negative pressure. This means that all of the intake ends up forced through the PCIe slot covers, which are perforated, because the GPU nearby is creating the only positive pressure, and so it's able to pull air in from the closest external part of the case. Meanwhile, the CPU can do poorly, despite the GPU doing well in this case, because there's limited air movement in the region of the CPU. That scales to every device. So the point is, you can't just point a thermal camera somewhere at the device and declare a temperature. It doesn't mean anything. It doesn't tell us anything about the interior of the device. And by the way, to address a common comment, it also doesn't necessarily mean it's cooling well just because it's hot on the outside. No, that's a pretty safe, wide claim to make, because in theory, something which is hotter externally should be more efficiently evacuating the heat from the inside. But it's not always the case, as we'll show you today. It could also just be cooler outside because it's cooler inside. There are uses for a thermal camera, even in computer hardware and testing. We'll go over those today as well. But as far as exterior temperature, the temperature of the body of this chassis doesn't much matter unless the plastic is in a range where it's starting to melt or where its integrity is being compromised by running too close to whatever the limitation of the plastic is. For water pump plastic, for example, that would be 60 degrees Celsius. It's probably a bit higher on this, but that's really the only area where it would be useful. Let's talk about incorrect use of a thermal camera. Even AMD and Intel have screwed this up in their marketing before, and it has irresponsibly led people to believe it's the right way to do things, for one, because Intel and AMD, so of course you can trust them because they're huge companies. They should know how to do this. But in reality, whichever one it was most recently that pointed a thermal camera at a heatsink, what they were trying to say is, look how cool our processor runs because heatsink. That's useful. It wasn't actually useful, spoiler alert, and it doesn't tell us anything about the temperature of the CPU underneath the heatsink. And that one we've complained about before because it sets an example for people to say, oh, this is how you're supposed to do it. But these engineering companies know better. So we designed an experiment with our standardized cooler bench and our standardized case bench to demonstrate the flaws of pointing a thermal camera at something several steps removed from the actual device under test. We ran multiple test passes of the Scythe Fuma 2 with thermal paste between it and the CPU, and without thermal paste between it and the CPU. Clearly, everybody at this point is in agreement that a thermal interface of some kind between your device which is extracting the heat and the device which is producing the heat is basically mandatory. Sure, you can smooth them perfectly flat and get them in good contact with each other, but realistically, almost every device has these microscopic imperfections on the surface where you need a medium to fill it. Otherwise, you end up with air gaps, where you have maybe 0.7 watts per meter Kelvin at 25C thermal conductivity of the air in those pockets where it's two surfaces which are imperfect, not mating together. So you need an interface. Everybody knows that, but we ran one test without an interface to prove a point. After multiple test passes with the internal dye sensor, the one that's accurate, that's actually in the silicon, we observed a pasteless result of 71 degrees T dye at 6.5 amps and 19.7 degrees Celsius ambient. The heatsink using a thermal camera was at 26 degrees Celsius. These are hugely different, of course. With paste, the measurement was 57.5 degrees T dye with internal sensors and 38 degrees on the cooler with thermography. This was tested at basically the same ambient, 19.6 degrees Celsius, and this was also at 6.5 amps. That's important. We do actively monitor every variable we can keep an eye on. So to make this even clearer, the CPU with paste was approximately 13.5 degrees cooler than the CPU without paste, and neither were throttling. However, its CPU cooler was about 12 degrees warmer. The proximity of these numbers is coincidental, the fact that they're on the opposite end of the scale here, but it's important to see that obviously the heatsink is hotter when the CPU is cooler here. Now again, that doesn't necessarily mean once you put all this in a case that the exterior of the case will be cooler if the device is worse, or the exterior of the case will be warmer if the device is better. It can mean that, but there's a lot more variables involved there once you get a chassis involved. At a heatsink to silicon level, or at least IHS to indium to silicon diffusion barrier to silicon level, these numbers make sense. So to reiterate the point of that chart, by logic of pointing a camera at the heatsink alone, someone would think that 38 degrees is hotter. And it is. 38 degrees is hotter than the other numbers. But the underlying CPU isn't necessarily also hotter, and so it's irrelevant. It doesn't matter what temperature the metal is. The copper and aluminum heatsink, as long as it's below 660 degrees Celsius or so, will not care what temperature it is. It doesn't affect its performance in a meaningful way. It can. It will change its performance characteristics as it heats up, but not at a scale of a computer part where you're talking maybe one cooler to the next, 10 to 20 degrees Celsius, absolute max difference. The component is getting its energy more effectively into the heatsink, and then naturally the heat has to come from somewhere in order to go somewhere. And that means removal and transfer. Just to be thorough, this testing was done with the controls on the screen, plus our standardized cooler testing methodology. All of it's public. We have documentation on it if you'd like to read more, but we're not going to go through it again here today. We control all test environments to the last variable that we have access to. And just to head off the comment of, well, but testing without paste isn't realistic, neither is pointing a thermal camera at something for an internal dye measurement. Because again, just to recap, the internal temperature of the silicon for anything, including an SoC in a PlayStation, has, in most cases, hundreds of sensors spread across the die, and they will present to you normally an average or a worst. You'll either get something like a junction hotspot, maybe an edge temperature, or an aggregate of basically all of the sensors. And ultimately, the steps removed you're looking at, you've got, let's take the PlayStation. In the case of the PlayStation, you have the SoC. The SoC internally is going to spread its heat across the silicon. It's relatively conductive, and some of that will go down into the substrate. Some of that will go down into the PCB through the ball grid array, which is mostly gold and copper and all of those components together. PCB's got a lot of copper in it, fiberglass, so it's going to spread down. It'll also spread up. On the top side, it's got the diffusion barrier. It then has, which is the coating on top of the silicon, makes it shiny. And then on top of that, liquid metal. On top of that, you have a copper cold plate. Sometimes some devices is nickel plated copper. And you're transferring all the way up to where you then take a measurement out here. You can see how that's too many steps removed to get accuracy for the device that actually matters, which is the SoC. And it's the same for a CPU, where with a CPU in a computer, you have extra layers too, where you might have thermal paste between the diffusion barrier and the nickel-plated copper IHS. Alternatively, you might have indium, and then a layer of gold, and then the nickel-plated IHS. One last note on the cooler test bench one too, before we move on to the case one. With thermography, the hottest thing in the bench when we used the thermal camera was the hub of the fan. So it's not useful data. 40 degrees Celsius fan doesn't really matter, but it's certainly not useful when you're looking at maybe a 60 degrees Celsius CPU underneath or the temperature of the metal for some reason. Let's look at another example. That one, the CPU cooler one, was something that we have actually seen from Intel and AMD. Hopefully now we don't ever have to say again that it's stupid when they do that. But now we're going to move on to something closer to pointing a thermal camera at a console. And this is going to be by using computer cases, something we have great control over. For this testing, we tested 3 cases with our standardized case testing bench and procedures. As a reminder, we now have about, well, more than 400 cases and configurations thereof tested with this hardware, so we have a lot of validation data. We tested the Torrent, the 500DX, and the Secura 500X. This gives us a range across, in order, great, good, and offensively bad thermal performance with the MSI case. We tested them properly, but we also improperly used the thermal camera pointed at various spots. First of all, here's a look at the thermography data from different parts of the case. So you can see how with a low resolution device, especially like a $100 camera with a narrow FOV, you point it at multiple places and you get different readings. If you don't have a controlled approach to doing this, it would be very easy to cut off even just maybe 1 inch of a device and end up with data that's significantly warmer or cooler than your previous measurement of another device. So even if we pretend that a thermal camera is completely acceptable for this type of analysis, once you get down to it, if there's not a control where you've got hopefully a good thermal camera with good resolution mounted to a tripod pointed at a fixed location on every device, you can't really compare the data. And especially once the chassis starts changing, the places that are hot and cool may move. So even if we pretend that data is useful, there has to be a control for where the data is taken. In other words, if you have one of these at home, you really shouldn't be just kind of like randomly moving your Seek or FLIR or whatever $100, $200 camera around, pointing it at things, because it's too chaotic. That's stated first. The maximum infrared reading for each device was 14 degrees delta T over ambient, so about 21 degrees Celsius for ambient there. And that was in the Torrent. It was 23 degrees over ambient in the 500DX, and it was 25 degrees in the MSI Secura 500X, which we basically called terrible thermally in our review. If you were to interpret this data as useful and take it at face value, you would think that the Secura, with these numbers, using the maximum thermography reading, is about the same as the 500DX. And you might then think that either one of them would be okay, because they're within a couple degrees of each other. You might also think that the Torrent is about 9 degrees better, whatever that means, in external temperature than the others. In this instance, the Torrent helps prove another concept. Although hot exhaust is an indicator of a device evicting heat efficiently, it isn't always. The Torrent has many places for air to escape. It doesn't concentrate in one area. And the PS5, by the way, also has heat escaping in more places than just where the fan evicts it. We showed this in our Schlieren imaging previously, where some of it kind of leaks out of the bottom. Additionally, the air simply doesn't get as hot in the Torrent because the internal ambient doesn't build as much, and that's a result of good design. It's getting the heat out and therefore not allowing it to build up as rapidly as in the other cases. Not that you get thermal runaway in any of these, but that's sort of the analog you would draw. If we switch now to a chart with the actual differences, you see how useless the thermography reading was here. Although the 500DX and the Secura 500X looked the same in the thermal camera, the 500DX internal CPU die temperature was 50 degrees over ambient, about 71 degrees in total, whereas the Secura 500X was 64 degrees over ambient. That's a massive difference. It's about 85 degrees if we factor in our ambient, so that's enough to lose TVB and PB2 headroom on modern platforms. If they were only 2 degrees apart, it wouldn't be enough to lose TVB at the beginning of the spectrum before it fully ramps, and you wouldn't lose as much off of PB2. So these are numbers that actually affect the performance, especially if you run with higher heat load hardware than what we're testing with here. Now for the Torrent, that was 9 degrees cooler than the 500DX here. This is conveniently aligned with the IR imaging, which also showed about 9 degrees. That's not because the temperature from the thermal camera is an accurate representation of the CPU temperature. It's an accident. And that's why the data is great, because what we can do now is we've created a scenario where we can get the CPU temperature difference to align with the thermal camera difference in this one specific scenario. And now we can say we've gotten the correct answer, at least in the delta, with the wrong formula. This is in the same way that in a math class, you can accidentally end up with the correct answer, but then you move on to the next problem, you try to use the same incorrect formula, and the answer is wrong. It was an accident the first time, there's a lot of numbers, you got lucky and you picked the right one, or came across it with the wrong formula. but it won't always work that way, and it was pure chance the first time. Additionally, still, it doesn't tell us anything about the actual characteristics of the CPU underneath, or how hot it's running. So let's pretend again that the thermal camera imaging is useful, is accurate, is a representation of something. If we assume all of that, we still don't have enough information if we say the temperature of this case is 25 degrees, the temperature of this one is 23 degrees, therefore something. We don't know what the therefore something is because we don't know the temperature of the device underneath. 25 might be totally fine. It could also be terrible. It depends on what the delta is between the point of measurement and the component which is actually thermally sensitive. In other words, if we measured the PlayStation 5 at, say, 60 degrees Celsius externally, we wouldn't have enough data to know internally if the CPU, the SoC, is anywhere close to an unreasonable, say, 90 plus degrees Celsius, where you're starting to risk longevity in terms of as the paste ages, it'll get worse. As it gets stuffed with dust, it'll get worse. Eventually you start hitting TJ Maxx and hitting a potential trip point or shutdown. We don't have enough, simply, to know if it's close to that, because it might be 60 externally, but if it's 80 internally, that's totally fine. So back to that chart, the red bar shows the difference in CPU internal sensor versus the thermal camera. The Sekiro was 40 degrees apart and the others were 27 degrees apart. It's not useful and it's nonlinear. And again, we're not really trying to talk about the Austin Evans video specifically. This is just talking about how thermal cameras work in general and trying to head something off before it happens in the future with anybody. Because if you point a thermal camera, and we've seen users do this on things like Reddit, but at an Xbox and then at a PlayStation, really what you need to ask yourself is, what did I just learn? That's the question. And it's a great question because the answer is nothing. And the concept of nothing is hard to conceptualize. So it's not a useful tool for that. There are great uses for a thermal camera. And one of them is to sort of figure out the rough area where there might be a thermal problem. So, for example, when we were first figuring out how to wire up the Xbox and the PlayStation with the probes, one of the things we cared about is where are the cool spots, where are the hot spots. You can manually wire everything, which, since you have a limited amount of thermocouples per reader, that's a problem. Or you can start eliminating a lot of the guesswork by pointing a thermal camera at it. You can do it externally. Okay, I know that this spot's kind of hot, this spot's kind of hot, so forth. And then you start popping off panels and working all the way down to the cooler. And now you can get a better idea of, all right, so it's these memory modules. These are clearly a problem. I'm going to wire these up for sure. Clearly the SoC I need without opening the device, we know that. And then the rest, you just kind of wire it up wherever it might logically make sense, and that gives a good picture of everything. So a thermal camera can be a great tool, but it has to be used the right way. It can't be abused to produce accidentally misleading data that everybody, including the test technician, might think is accurate because it was presented as such. So it's a tool basically to figure out what other tools to use and place on the device. Great use is for video cards, by the way, especially if they don't have a backplate. But removing the backplate or using it on one without a backplate allows you to see the VRM layout, you can see the memory placement, and you can see the GPU. And all of these things you can figure out by looking at it if you're experienced with looking at a board. But the important thing is that by looking at the thermal footprint, so to speak, it helps to very rapidly narrow down, okay, on the flip side of this, I want to put the thermocouple on MOSFET number 3 from the top because it's running really hot in thermography. And then you rapidly narrow down, clearly the memory module down near the PCIe slot is running the hottest out of all of these. This is the one I care the most about because it doesn't matter what temperature the other ones are if one memory module is running close enough to eventually be a point of failure. We don't care if they're all running at 80 if one's at 110 degrees. All we care about is 110 degrees because we're looking for failure. So thermal cameras are great tools, but they need to be used with the right frame of mind to then basically get you to another tool, which is a pain in the ass to use. Thermocouples are a nightmare to wire up, especially once you start getting into potentially 8 of them for a device, but it's the right way to do it. And unfortunately, that's the way you have to do it if you want it to be done right. There are other considerations with thermal cameras too. We're not gonna get into them today, but things like reflectivity of a surface. So for example, if you're trying to quickly figure out where a case might be hot, pointing a thermal camera at the side of it doesn't necessarily help. It can. It has to be done right. You use a special material for it. But if it's just pointed at an acrylic panel, sometimes a glass panel, what you end up with is the reflected heat of the room. So there's times where we've shown this in the past, can't remember what video, but where you can wave your hand around. So you've got the case over, you have the case here, you have a clear side panel on it, you've got a thermal camera back here, let's say on a tripod pointed at it, and then someone is standing behind the thermal camera, not in front of it, not in between the two. They're standing behind the thermal camera, and what you see is a reflection in the glass of that person, thermally, from the thermal camera. And that's because reflectivity is a thing. You can see it with the hand being reflected sometimes too. So that's a problem. You're not actually seeing the inside temperature behind the glass. You're seeing the reflected temperature to an extent. It's not really accurate, but that's sort of what you're getting. Same is true with emissivity as a problem. If you stick to things like black body objects, surfaces that have been accounted for with the emissive calibration in a good thermal camera, you're okay. But emissivity is an issue, reflectivity is an issue, proximity is an issue. Thermal cameras' accuracy changes, its number changes as you move at different distances. So if we take a measurement of the PlayStation 5 from here versus from here, we're going to get different numbers, especially on one of those $100, $200 cell phone thermal cameras, and just not meant to be used that way. So the cell phone ones, they're fun toys that can provide an initial idea of where to investigate something. Might be useful if you're trying to find if you have in-floor heating. Linus did a great example of this recently. He used it to kind of identify where, I don't know how those work, but where the heat was being run, basically. So they can be useful. Use it the right way, though. That's it for this one. Thanks for watching. As always, very strong reminder here, two things. One, it is possible to get the correct answer accidentally. We're saying that in case the numbers end up being 3 to 5 degrees apart, but it can be an accident, and it doesn't tell you the temperature of the device. Two, this is not meant to be like a direct Austin Evans response or like Austin Evans is wrong or whatever. We're saying explicitly it's very possible he was right, and his conclusion explicitly, again, may be entirely correct. And the video, it doesn't seem like he really had any other intent than to just kind of quickly test it, which is all fine. So just a reminder, there's no really point to beating the guy up or brigading him over something. And if you are, it's probably because you've got your own intentions in the wrong place, which is you want your device to be better than the other person's device. So maybe cool it on that front. From what we've seen, it's gotten way out of control. It's totally undeserved. He doesn't need to go through all that. And we've been on the other end of that for other stuff, so we know what it's like. But we'll look at it in full detail properly. We've got both devices coming in. We'll be working with Digital Foundry. We're getting one of their PlayStations in. That will allow us to wire it up and do in-depth testing. There's not going to be a response to Austin or anything like that. It's just going to be a, here's the numbers we collected. This is kind of cool. Here you go. So that's it for this one. Thanks for watching. Subscribe for more. As always, you can go to store.gamersnexus.net or patreon.com/gamersnexus if you'd like to help us out directly. And we'll see you all next time.